Hello, in this video I'll be showing you basically a proof for a trigonometric identity that I used in a previous video to show that the differential of sine x is equal to cos x. So in this video is just basically a proof video to understand, well, to show you where this limit comes from. So in my previous video when I was showing that dx of sine x is equal to cos x, I introduced this particular limit. So the limit, as I used h in this video, but in this video I'm going to use theta. The limit, it doesn't really matter as long as you have a symbol and you know what the symbol means. The limit as theta goes to 0 of this limit, sine theta over theta, is equal to 1. So I'm basically just going to show why this is true and where does it come from. So I'm just going to put this limit in the corner up here so we remember what this video is all about. And basically I'm just going to derive it and why it's true. So first off, I'm going to draw myself a set of axes, and then I'm going to draw the unit circle. Oh, that's a terrible start to a circle. Oh god, this will be a while. Sorry guys. Okay, that's good enough. I'm just going to draw the other side now. Okay, so this is the unit circle. So the word unit in math means 1. So this is a circle that has a radius equal to 1. So this length here is 1. This length here is 1. I know this side of the circle is pretty bad, but let's pretend it's a pure circle. Okay, so the only bit of information we need is just on the right hand side of the circle. So we're going to draw a diagram here. So we're going to have a line extend to here. This can be the radius, and we're going to have we're going to let K be a point on the unit circle, and we're going to have another point here on the x-axis, H, where H is a point where this is a right angle. So you can have this point here too. This angle here is going to be theta, and we're going to have a tangent line at this point A, and A is the point 1, 0, and we're going to have a line that goes just straight up from this point here. So it's exactly tangent to the circle at this point. And we're going to extend this line, we have this named O, so this is the origin. So we're going to have the line O to K intersect this tangent at this point here, L. And now we're going to start basically deriving some stuff. Alright, so we're going to define theta as the angle KOH. So the angle KOH is theta. That's what theta is defined as. Okay. I'm just going to get rid of this side of the circle because we don't really need it. Pretend we do have the rest of the circle though. Alright, so that is what theta is. Theta, if you see this symbol in math, and it has KOH, this symbol means angle. Okay? Mine looks like an L right now, so I'm going to try and make it as the best as I can. There. That means angle. Alright? H is a point on the x-axis such that the angle H is a point. This is our x-axis and our y-axis. Is a point on the x-axis such the angle KHO is a right angle. Okay, so what does that mean? It means that the triangle it means that the angle, the KHO, so K is here, H is here, and O is here. That means that this is a right angle. And if that's a right angle, we know that if we have a right angle here, this whole thing needs to be 180 degrees. Therefore, this is a right angle here too. Alright? So know that, know that, know that. Okay, I'm just going to put this bit of information in the corner somewhere. H is a point on the x-axis. I'll move this over here so we don't get confused. Unit just means 1, radius 1. Right? And basically, we want to find an expression for this triangle OKA. So there's a triangle here. So I'm just going to draw another line there. The point A is 1, 0. We want to find an expression for the area of the triangle OAL and an expression for the area of the triangle OAK. And we also want to find an expression for the area of the sector OAK. Right? So we'll start off with a sector. So the area of so what is a sector? The sector O A to K is basically this little arc, this little thing here. So I'm just drawing a better picture of it. It's this area here that you see between O, A, and K. It's that thing here. The area of the sector here is half of theta. Okay? So we have that done. So that's the area of a sector. I'm just going to move that information over here. Oh, whoopsie daisy. So the area of sector OAK is a half of theta. Okay? You might have seen that in textbooks for sectors. Because that has a length of 1 and that has a length of 1, so the area of this is just a half of theta. Okay. Now we need to find an expression for the area of the triangle OAL. Actually, let's do OAK first. So I'm just going to get rid of this so we have a lot more room. So we're going to do this one now. So what is the triangle OAK? That is going to be this triangle in here. So it goes from there to there to there. Right? So I'm just going to draw it over here, what we're actually looking at. We're looking at something like this. H, theta, O, K, A. Right? Alright. So recall the area of area of a triangle is a half base times height. So the area is going to be the length of OA multiplied by HK times a half. Okay? Because that's the height and that's like the biggest length. So the area of the triangle, I'm just going to use triangle for the symbol triangle. Which one are we finding? We're finding OAK is equal to a half times OA times HK, where H is a point, is this point here. So I'm just going to, is that point there. So what is, now we've got to find what these actual lengths are. So recall this is the unit circle, so this has a length of 1 here, okay? And this is opposites of this angle here. So that's opposite this angle here. Recall that sine theta is opposite over hypotenuse. Okay? The hypotenuse is 1. So if we move that over there to get opposite by itself, we'll have the opposite is equal to 1 times sine theta. So the opposite is the length hk. So therefore the length of hk is just sine theta. So rubbing this all out, rubbing this all out, we know that the height of this triangle here, this height here, is sine theta. Okay, so we can replace, start writing out this again. So 1/2 times OA times sine theta. We know that the point A is also on the unit circle, and the radius of the unit circle is 1, so the distance from O to A is just 1. So we can just rub out OA and just put 1. Okay? So now we have an actual expression for the area of the triangle OAK. Okay? So I'm going to move all of this stuff here over here. And I'm going to rub this out. Okay? So we found that. Now we need to find an expression for the area of the triangle OAL. So the triangle OAL is going to be, so I'm just going to rub out this, whoops. It's going to be, this is going to be OAL, which is this point up here. Alright, so I'm just going to redraw a triangle. So it's out of our diagram. So this is O, this is still theta, this is A, oh, this is A, not O. That's A, and that's L. Okay? We know this length here is 1, because O to A is 1. We want to find this height here. We want to find the length of AL. Using trigonometry, we know that tan theta is equal to opposite over adjacent. So therefore, we want to find the opposite, okay? And we know that the adjacent is equal to 1. So if we move that up there, we'll have the opposite, which is the length of AL, is equal to 1 times tan theta. Okay? So area of the triangle is 1/2 times 1 times tan theta. Okay? So rub that out now. And once that's all gone, we've got an expression for the area of the triangle. Which triangle was this? This is the triangle OAL is equal to 1/2 times 1 times tan theta. Okay? Now you're probably wondering, why did we need to set up all of these expressions for these triangles and areas of sectors to prove this inequality, this limit up here, right? Well, looking at our diagram, we can see that the area of the triangle OAK is less than the area of the sector OKA, so it's less than 1/2 theta, and that is less than the area of the triangle OAL. Triangle OAL. So finding the areas of these things, we can set up this inequality, which we can then use to create this limit. Okay? So the area of the triangle OAK is a half times 1 times sine theta. That middle bit is still a half of theta. And this end bit is going to be a half times 1 times tan theta. Okay? So I'm just going to move my diagram because it's getting in the way now. I'm going to move him up here. Boom. Alright. So simplifying this whole inequality, we have a half sine theta is less than or greater or equal to a half of theta, which is less than or equal to a half of tan theta. Divide all of these by half and you get this inequality here. Sine theta is less than or equal to theta, which is less than or equal to tan theta. Okay. Now we're actually getting somewhere. This is starting to look a bit more trigonometry-ish, okay? Rather than areas and stuff, right? Now, the angle we're looking at is only in the first quadrant. So theta belongs between 90 degrees or pi over 2 and 0. So theta can only exist in these bounds here because it can only be from here up to here for these triangles to still exist, okay? So those are the bounds of theta, right? So what we're going to do now is we're basically we're going to divide our entire inequality we've got here by sine theta. So we're going to divide this by sine theta, and can divide this by sine theta, and we're going to divide this by sine theta. So we're left with 1 is less than or equal to theta over sine theta, which is less than or equal to so tan theta is equal to sine theta over cos theta. So when you divide by sine theta, you're timesing by sine theta on the bottom, and it's cancelling with the 1 on the top. So we're left with 1 over cos theta here, okay? Now we're going to look at what happens when theta approaches 0, right? This is starting to look like a limit up here. So these less than or equal than signs, they're pretty much equivalent. Because we're dealing with like limits now. We're dealing with a limit. So these less than or equal than signs are pretty much the same as just equal signs. So we can find out, I've run out of room actually. I'm going to make all of this tiny so I can write up here. Okay. So we have 1 over theta over sine theta, 1 over cos theta. I'm going to rub that out. Now we wanted to prove that the limit of theta going to 0 of sine of theta over theta is equal to 1. Well, let's see what happens if we have 1 over cos theta. If we have 1 over cos theta, and let's say theta was equal to 0, cos of 0 is 1. So therefore, this, when you apply this limit, the limit when theta goes to 0, is equal to 1. Right? So therefore, this statement on the right hand side is also equal to 1. Okay? Actually, let me just flip this again. I can do it a better way to make it look like how we've got it. We can flip the reciprocals of all this stuff here. So we can go, we can flip them all over one another. So we can rewrite this as 1 over 1, that stays the same, over sine theta over theta is less than or equal to cos theta over 1. So if you approach the limit as theta goes to 0 of sine theta over theta, that is equal to 1. Because when this goes to 0, that is equal to 1. Okay? And theta, yeah, that's pretty much the proof for this limit. I hope you kind of understood this. I know this was a pretty hard video to understand because this is a geometric proof from nothing. So that is pretty much the geometric proof that the limit as theta approaches 0 with sine theta over theta is equal to 1. Alright, I hope you understood this video. If you have any questions, leave some in the comments. They will never ask you to derive stuff like this in an exam. This is purely for understanding purposes. Alright, thank you for watching. I hope you enjoyed.